Hello students, welcome back. After a very long time, I'm back again with the next set of series of lectures for 12th Science. So in today's session, we shall begin with something very interesting. I shall be telling you all about something that we can see, feel or touch. It has got mass and it occupies space. I'm sure most of you all would have guessed that anything that can be seen, felt or touched having mass and occupying space is nothing but matter. Yes. So we shall delve deep into matter today. Now this matter, as you have already learned in your lower classes, can be classified on the basis of the intermolecular distance as well as the intermolecular forces into three types. That is, you can have solids, liquids and gases. Now, what do you understand by intermolecular distance and intermolecular forces? So, if you look at this solids, the diagram represents that the solids are having the particles closely packed in with each other. They are so compactly arranged that the distance between two molecules is very, very less, or we say the intermolecular distance is the least in solids. On the contrary, if you have a look at the gases, you will see that here the particles are very far flung. They are very far away from each other. That is, the intermolecular distances is more in the gas, or rather I should say it is the maximum in a gas. Comparatively, in liquids, the intermolecular distance or the distance between adjacent particles of the liquid is more than that of the solids, but it is less than that of the gas. So we can say the intermolecular distance in a liquid is moderate. And because of this intermolecular distance, we can decide the extent of force that exists between the molecules. So since the particles in a solid are very compactly arranged, having the minimum intermolecular distance, therefore the intermolecular forces of attraction between them will be the maximum. Whereas in gases, the intermolecular forces of attraction or repulsion, whatever they may be, is going to be the minimum since the particles are very far away from each other, having maximum intermolecular distance. Therefore, intermolecular forces are weakest in the gases and maximum in the solids. In liquids, it is again moderate. The intermolecular forces will be less than that of solids, but more than that of gas. Right? Now, with this knowledge, let us move ahead and see more in detail about solids. So, in class 12, the very first chapter deals with solids. Now, this solid can be further classified into two types, that is crystalline and amorphous. Now, the general properties of solids you have already learned in your lower classes, right? So, I am directly going into the crux of the chapter, that is, you can classify the solids into two broad categories as crystalline and amorphous solids. Now, what do you understand by crystalline and amorphous? So, as I just told you all, in the solids, the particles are compactly arranged. That means having the least intermolecular distance and maximum intermolecular forces of attraction. But if this order in which the particles are arranged close to each other is having some definite arrangement, so you can see here the particles of this table salt that we consume daily, they are having a orderly arrangement. They form a particular pattern or a design, right? So thus this is an example of a crystalline solid. So table salt, even otherwise we say there are crystals of the salt, right? So this crystal word comes from this arrangement of the particles within the solid. On the contrary, if you have a look at the cotton candy, which you enjoy at the fairs and at the melas, okay, so that cotton candy is made out of sugar. So after that sugar is crushed, it is converted into the fluffy cotton candy. So this cotton candy is where the particles of the sugar are no longer compactly arranged. I mean, they are compactly arranged, but not in a particular pattern. Okay, you cannot see any definite arrangement of the particles here. So this is an example of an amorphous solid. All right. On the contrary, sugar is a crystalline solid. Now see here, one more arrangement of particles which you can see in diamond. So this diamond is a crystalline solid very much sought after for its shine and for its luster. So how does this property of diamond come? It is because of the well ordered and definite arrangement of the atoms of carbon in it. Okay, so in crystalline solids, whatever the constituent particles, whether it is molecules or atoms or ions, they will be having some orderly arrangement, a definite pattern of arrangement of the constituent particles. So here you can see a comparative picture of a crystalline and an amorphous substance. So on the left hand side, you can see quartz, that is crystalline SiO2, whereas on the right hand side is glass, that is amorphous silica. So in the quartz, you can see the pattern of arrangement. There is a regular repeating pattern of arrangement of the constituent particles of silica and oxygen. The red dots denote the silica, whereas the blue ones denote the oxygen. On the contrary, in glass also, the composition is the same. Glass is also made up of silica and oxygen atoms, but there is no definite orderly pattern or repeating structural arrangement of the particles here, right? And that is what differentiates the crystalline substance from the amorphous substance. Now moving ahead, there is one more characteristic of crystalline substances that is known as anisotropy. Now what is anisotropy? Now depending upon the arrangement of the particles, there are some physical properties like for instance refractive index which changes with the change in direction of observation. For example, if I were to study a property in the direction of this path A, then you can see the arrangement of particles are different here. There is only the pink colored atoms here. Whereas if I look at the same crystalline solid in a diagonal path, that is the path B, then the arrangement is slightly different. There are alternate atoms of different kinds, the green and the pink atoms. Okay, so due to the difference in the arrangement of the particles based on the path in which I'm observing or the direction through which I'm observing or studying that physical property, the value of that physical property also is going to change. So a refractive index is one such example. So this characteristic of bringing about a change in the value of a physical property with change in direction is known as anisotropy, and this is a characteristic of only crystalline solids. Whereas in amorphous solids, even when there is a change in direction, okay, now look at this. If I follow the vertical path, that is path A, the vertical path, the particles are at random over here. There is no orderly arrangement. So you can see a cluster of green and pink atoms over here. And even when I take a diagonal path across this line A, then also we see a similar cluster of different atoms of green and pink. That means irrespective of the direction in which I'm going to measure a particular physical property, there is going to be no change in the property with direction. So when the solid does not show a change in the value of a physical property or the magnitude of the physical property does not change with respect to the direction, that is called as isotropy. So isotropy is a characteristic of amorphous solids, whereas anisotropy is a characteristic of crystalline solids. It is as simple as imagine you are all standing for a mass drill. Okay, so there is a row of girls and a row of boys. So when I stand in the front and look at you all, I can, if I see from the front to the back, I will see a single row of girl and then a single row of boys alternating with each other. But if I look through it diagonally, then I will see girls and boys standing alternate to each other. So if I want to say from the front, if I say I will say or single there are rows of a single gender. But if I look at it diagonally, I will say that no, there is a row of mixed students, girls as well as boys. So the property changes with the direction. But imagine the same set of students are now in the dispersed state. That means it is your break time and all are just gathered on the ground and running here and there. So then if I'm standing in the front and observing you, or if I observe you from the corner of the ground, it makes no difference. I will still see a similar set of students, a mixture of girls and boys in both the directions. So that is the basic difference between anisotropy and isotropy. So anisotropy is when the properties, the physical properties of a solid changes with respect to change in direction. And isotropy is when the magnitude of a physical property is not affected by the change in direction. Okay. Now, moving ahead, there are still some more characteristics which are specific of crystalline solids. For example, the word isomorphous. Now, what do you mean by isomorphous? The iso suggests it is same and morphous means structure. So when you see two or more crystalline solids having the same crystalline structure, they are said to be isomorphous with each other. For example, if you compare the structures of sodium chloride and magnesium oxide, then you will see that both of them have got a similar crystalline structure. Although the composition is different, but the ratio of the atoms are the same. So since sodium chloride and magnesium oxide exhibit the same atomic ratio of 1 is to 1, therefore their crystalline structures are also similar. Similarly, in case of calcium carbonate and sodium nitrate, the atomic ratio calcium is to carbon is to oxygen is 1 is to 1 is to 3. And similarly in sodium nitrate, it is 1 is to 1 is to 3. Sodium is to nitrogen is to oxygen. So since the atomic ratios are similar, the crystalline structures are also similar for calcium carbonate and sodium nitrate. So these substances are said to be isomorphous with each other. But it is not necessary that all examples where you see the atomic ratios are similar will have the similar crystalline structure as well. For example, if you compare NaCl and KCl, the ratio is the same, 1 is to 1 in both the cases, but they do not exhibit isomorphism. Okay, it's only certain substances which are having the same crystalline structure, um, and then they are said to be isomorphic with each other. And it is observed that the substances that are isomorphic with each other generally have the same atomic ratio, although the vice versa is not true. Okay. Now coming to the next property, that is polymorphous. Now isomorphism is different from polymorphism. What is polymorphism, or what are polymorphous substances? Poly means many and morphous means structure. So if a single substance exists in multiple forms or in more than two forms, then it is said to be polymorphous. For example, quartz and quartz, that is alpha and beta quartz, and cristobalite, these are the polymorphic forms of silica. Okay. So a single substance silica is existing in more than two or three crystalline structures. So silica is said to exhibit polymorphism. On the other hand, if this substance is an element, okay, if the substance is an element and the element is able to exist in polymorphism, or it is exhibiting more than two crystalline structures, then the property by which the element is exhibiting two or more crystalline structures is called as allotropy. Okay, so for example, you're already aware of the allotropic forms of carbon, which is graphite, diamond, and fullerene. Now, this brings us to the differentiation between crystalline solids and amorphous solids. So, what are crystalline solids? We have understood that crystalline solids, there is a regularity and periodicity in arrangement of the constituent particles. Okay, the particles have a definite arrangement or an orderly arrangement, giving rise to a definite pattern. Okay, whereas in amorphous solids, the constituent particles are just present at random. There is no orderly arrangement of the particles. Okay, it is like when you draw a rangoli, or rangoli using dots, then the set of dots, the pattern which is formed in one set of dots keeps on repeating. That is what happens in a crystalline solid. Whereas in amorphous solid, you could imagine it is a freehand pattern that you have drawn. Okay, so there is no definite repeating pattern over here in amorphous solids. Then the crystalline solids, because of their orderly arrangement of particles, the melting points are very sharp. That is the point at which the solid will get converted into liquid. The bonds between the atoms are going to break, or between the molecules are going to break. Okay, that is going to be very definite or precise. So they will have sharp melting points. On the contrary, amorphous solids will melt over a range of temperature. All right. Then the crystalline solids are said to be of long range order, because when you look at a crystalline solid, the orderly arrangement of particles repeats over a long distance. Okay, over the entire solid, whatever amount of sample you may take of the crystalline solid, the repeating pattern is observed for large distances. So it is said to be of long range order. Whereas amorphous solids, if at all you happen to see a pocket of orderly arrangement, it may be repeating only in some places. So it is only of a short range order. It will not be continuous over the entire solid. So the amorphous solids are said to be of short range order. Then we saw that crystalline solids are anisotropic in nature, that is, they exhibit the property of anisotropy, where the magnitude of the physical property changes with change in direction, example refractive index, whereas amorphous solids are isotropic in nature. Okay, you can add on to this list of differences. When you cut up a crystalline solid, you will see that the cleavage will give rise to smooth surfaces. It is like when your mother makes a barfi at home during Diwali. Okay, if the burfi is smooth and she cuts it, you will get a smooth cleavage. The edges are smooth. But suppose the burfi was made and with some nuts cracked, I mean scattered into it. Okay, it is like your fruit and nut dairy milk chocolates. So when you try to break it, you won't get smooth edges. The edges will be rough. Okay, so in amorphous solids, upon cleavage, the edges are rough, whereas in crystalline solids, the edges on cleavage will give you smooth surfaces or smooth edges. Then next, the properties of polymorphism, that is a substance existing in two or more crystalline structures, and isomorphism are characteristic only of crystalline solids because only they exhibit the regular arrangement of particles. Whereas amorphous solids, you will not find this polymorphism or isomorphism. So I hope this has been a very interesting session for you. So this was an introduction to the solid state. I hope you keep looking forward to my upcoming videos to get into the details of this particular chapter. So until then, thank you and have a great day.